to the second half of the exam. I think hopefully what you saw was my focus is on how to be effective users of these things, right? So you have to know kind of enough about how they work to know their benefits and drawbacks, and what knobs we have to tune, right? And we need to make sure that we're identifying like the right tool for the job. So that's kind of that's what most of the questions are focused on, and I just wanted to clear up some misconceptions. So starting at number 6, so I have some data here, right? I'd like to be able to do predictions based on this data. So what type of problem am I dealing with here? So I have data of two y values. Yeah. So what would we call the problem of trying to take an input and predict whether it's one of two values?
Classification.
So this is a classification problem, right? And so we're looking at the various techniques we could use to try to classify points. Okay, and so the question asks you to compare linear regression versus logistic regression. So a few people said you can't use linear regression for this, which is not true, right? My linear regression will give me a line that looks like this, right? I can use this for classification, right? How would I use it for classification? It's actually the same thing I do for logistic regression.
Above the slope of the line below.
Sorry.
I guess like above and below like the plane.
Well, so like, my input x, right? I don't know how high it is, so I can have any x that's above the line, right? So if my x is over here, I can pick a y that's above the line, but I don't know what the y should be. That makes sense. So I somehow, given a new x, I can figure where on this line I am. How am I going to use that for classification? How do I say, take a point on this line and say yes or no, like 1 or 0? I just pick a threshold, maybe right here. Right? I plug my x into this line equation. I get a point on this line, and I just see, is it above the threshold or not? Which is the exact same thing I do with logistic regression, right? I plug my point into the equation, I get a point on the line, I compare it to a threshold, and I use that to say whether it's true or not. Okay? So I can, both of these methods sort of work the same way. Right? But this sigmoid curve here is actually a lot nicer to work with for classification tasks. So what's special about this sigmoid function compared to this line that I've drawn here? And, I mean, if I pick my thresholds to be the same, I would get the exact same predictions out of both of them. And so depending on how I solve for my line, right, I could get the exact same predictions out. Why would I prefer to use logistic regression? What's like the killer selling point that we talked about? Yeah, so the biggest thing here is the logistic regression. I can interpret the output as the probability of being in one of the two classes, right? And because it goes from 0 to 1, right, I have a natural cutoff value of 0.5, right, 50-50 chance of being in either class, right? And the value tells me the probability of being in one of the classes. Right? So it helps with the interpretability, right? Whereas my linear regression, no, I have a value of negative 10 million. Well, that doesn't really tell me anything. So that's the kind of the killer selling feature for the logistic regression, is I can interpret the output as the probability, right? So I get kind of more information out of my classification. Does that make sense? The next one, the printing part was hard, but the key idea here is that an SVM allows you to model a decision boundary that's not a straight line, where the logistic regression, it's going to be a straight line. We talked about logistic regression. We're fitting something like this, and we can rotate it, and we can stretch and bend it, but we can't curve. We can't curve this in like the horizontal. What's another algorithm we could have picked on that data set where we had a curved decision boundary? Another classification algorithm. We talked about like 3 or 4. So yeah, SVM, KNN, right? Can we capture curved decision boundaries with KNN? Yeah, right. KNN can do all sorts of crazy stuff, right? It just depends on what data we happen to have near the boundary. So SVM or KNN are going to do better on this one because the decision boundary is curved. Next one was about the knobs we have to work with KNN. So we can actually just look at this 1D example we have here. Okay. So if I make K really big, and I do KNN classification here, what kind of outputs am I going to get? Everything's going to be the same, right? I'm just going to count up whether there's more 1s or 0s in my output, and then it doesn't matter where I predict because I have the same neighbors everywhere. Right? If I make my K really small, if I set my K to 1, what's going to happen? I have overfitting, right? I'm going to have predict 0, 0, 0, 1, 1. I have all these weird jumps everywhere where there's outliers. Okay. Okay. So in the example where K is really big, what would we call that? It would be underfitting, right? My model is not complex enough to describe the data, right? The model that I'm coming up with is that my data is constant, right? And that's not true. If I have a really small K, that would be overfitting, right? I'm fitting in the noise of my data, not the true nature of what's going on. So if I am overfitting and I do cross validation, what would I expect to see?
Very well on training and very bad on testing.
Yeah, so if I overfit, right, my training accuracy is going to be perfect, right? If my K is 1, every time I look up a training point, I'm just going to ask what the class is at that training point, and I'm going to get every single one right. On a testing point, if my K is 1 and I ask for a point here, right, probably I should classify it here, and I'm probably going to pick here just because I'm fitting too much noise. Okay? So when I'm overfitting, training accuracy is going to be great, testing accuracy is going to be bad. Okay. What happens when I underfit? They'll both be bad. Or if I just say, okay, everything's a 1, I'm going to do bad on my training set because I'm going to miss all these points, and I'm going to do bad on my testing set because I'm going to miss the same kind of points. All right, so that's my knob here. A lot of people talked about, or kind of confused this with k-means clustering, okay? Which works kind of the opposite. So when I'm clustering, when I make a big K, what am I doing? I'm overfitting, or I'm putting each point in its own cluster, more or less, right? So that's overfitting, right? If my K is really small, I'm putting all the points in the same cluster and I'm underfitting, right? So the parameter name is the same, but it's the opposite problem, right? Versus for K and N versus clustering. Right. So we'll ask the same question. Number 9 is basically the same question for SVMs. Okay. I have this knob C. What if I make C really small? What happens with my SVM model? It overfits. Right. So remember, the C controls basically the thickness of the separating region. If I make C really small, then I'm only going to be considering points that are right next to the boundary, right? And I'm going to be really sensitive to those points on the boundary, and I'm going to kind of ignore everything else, right? So I'm going to overfit. I'm going to get a really wiggly line, right? If I make my C really big, that boundary region is going to be really thick, right? I'm going to consider more points, and it's going to kind of smooth everything out. So a few people said something like the I think it was increasing C would increase our accuracy or something. Right? It's not that simple for either the training or the testing data set. Right? For the training data, yeah, a really small C, we're going to increase our accuracy on the training data. But on the testing data, that's absolutely not going to be the case. When we looked at varying C, does anybody remember what the graphs kind of look like? We just plotted like C versus the training, versus the testing accuracy. It tended to look something like that. Okay. When we're overfitting, right? Our model is too wiggly; it's fitting noise. Right? When we're underfitting, we're not capturing the details along the boundary well enough, and so we miss that weight. So again, like maximizing this knob in either direction is not a good thing, right? We have to find the sweet spot where we're not overfitting, we're not underfitting. Number 10 seems to be the hardest one on the test. So we'll talk through that one. So what is clustering? What is the goal of clustering? So we're trying to understand our data. We're breaking it into groups of data points that we assume are similar somehow. Right? And is it supervised or unsupervised? Unsupervised. Right? And what does that mean about our evaluation of this? It's hard, right? There's not really a right answer generally. Right? I mean, if you're Netflix, right, you're trying to cluster your customers, there's not you don't really, there's 10 different types of Netflix viewers. No, you have no idea. You're just trying to figure out who is similar. Right? So in general, right, we don't know what the right answer is. However, it can be convenient to run clustering on data sets where we know there is a right answer and kind of see how well we do. The handwritten data, or handwritten digit data set that we used, right? How many clusters should there be in that data set? If it were letters, yes. For digits, right, it should be 10. Right? We know there should be a cluster for 1s and 2s and 3s and 4s and 5s. Right? Right? So if we run our clustering algorithm with 10 clusters, right, we expect that those should match pretty closely to the labels that are a part of that data set. Right? And when we go to evaluate this, we realize that it's actually pretty hard to evaluate. right? How come, I have my 10 clusters, I have my 10 labels. Why is it hard to do an evaluation to see, how well my clustering algorithm is? So my clusters, the only information I have about them is which points belong to them, right? Or maybe a little bit extra information. Do I have any information about what digit they're supposed to represent?
No.
Not directly, right? I could try to infer it from the points that are there, right? But I don't know that this cluster is supposed to be 8s, or this cluster is supposed to be 6s, or this cluster is supposed to be 7s. So even when I know what I expect my clusters to be, because I chose a data set where I have some extra information, I don't know how they're, like the clusters are random, right? If I use k-means and I throw down my random points to start with, there's no reason that my first point that I throw down should be near the zeros at the end, right? There should be no relationship between the cluster, index and the label that I hope all of the members have. Does that make sense? Okay. So this clustering, there's no notion, my clustering algorithms don't know anything about the labels that I'm kind of hopefully matching as I evaluate this method. So the homogeneity and completeness are kind of two ways to try to estimate that or infer that. Okay? And they both look at basically, which labels belong to which clusters. So does anybody remember what that homogeneity, specifically what that measured? Yes. So if I'm I look at my clusters, I look at which labels belong to the points in that cluster, right? And the homogeneity measures, are they the same or not? Okay. So if I have a cluster and 95% of the points that I put in there are labeled 2, that has, good homogeneity. Does that mean I classified all the 2s correctly? Not necessarily. How could I get really high homogeneity with 2s and still not actually be a very good clustering?
What's all the zeros and 2?
So the homogeneity tells me that's not happening, right? Because my cluster is mostly 2s.
You could have half of 2s.
I could have half of the 2s in one cluster and half of the 2s in another cluster, and maybe I mix the 8s and the zeros together. Right? So homogeneity means, okay, all of the points in the cluster are the same label. Completeness goes the other way. It says, okay, all the points with the same label should be in the same cluster. Okay, so my completeness, I look at all the 2s for my data set and say, okay, are they in the same cluster or not? Okay? And so that's a way to kind of to try to match the clusters to the labels when there's not a direct connection between those. We can just only try to infer what that relationship is, and so that's how the homogeneity and completeness scores come up with that. Okay. So yeah, I think it seemed to be the trickiest one on the test. Any other questions about that? And the last one, the NLP question. This one also seemed to be kind of tricky. So this question asks you to use bag of words on this natural language data set. What did the bag of words model actually do? I may remember what we actually, we went through this whole sentiment analysis thing. Only a small part of that process was bag of words. So which part of the process was the bag of words taken care of?
Like a whole group of books or whatever, and checking the first, or checking the most common 1,000 characters or something similar, and then going through each individual book and seeing if they include those 1,000 characters.
So I build my bag of words model with all of my books or all of my training data. Okay. I try to run a single book through my bag of words model. What is the output? What do I get? After I take Moby Dick and run it through bag of words, what is the output? What do I get?
That's the way of Boolean.
Yes, exactly. What I get is a big vector with a 1 in the whale row and a 0 in the spaceship row and a 1 in the Ishmael row and a 0 in the Hermione row, whatever. Okay. Okay. So the bag of words takes a book and gives me a vector that describes that book based on what words appear in it. Okay. Does this tell me about sentiment or classification or anything like that? No, this is just a vector. If I want to do classification, okay, so first off, what type of problem are we trying to solve here in this NLP problem? It's a classification problem, right? We're taking a data and we're trying to figure out what label corresponds to it. Okay. Do we know the labels ahead of time? Yeah, right? The publisher knows what types of books there are, right? We have labels, right? So this is a classification problem. I have a bunch of points that look like this. I want to do classification. What tools do I have? You could use a SVM or KNN, right? Right? So the bag of words, right, is how we translate a book into a vector, right? A lot of people said things like, look at the words and then compare them to see what genre it's in. That, so you're kind of vaguely saying do classification, but not saying like how you would go about doing it or what kind of algorithms you would look at or how you even do this comparison. Right? This is the key part, right? I turn my data into points, just all the points are the same dimension, right? And then I can use any of the classification algorithms we talked about to do this classification. So yeah, the key idea here is we have one step to turn NLP into just boring vector data, and we talked about bag of words for that, right? And once we have boring vector data, we can just use normal classification stuff. Other questions about the exam? Okay. So today we're going to talk about another unsupervised learning problem. That's kind of the last kind of general data analysis problem or task that we'll talk about. And starting tomorrow, we're going to talk about how we can use neural networks as a method for performing the various tasks we talked about. So regression, classification, dimensionality reduction. We'll see how instead of using logistic regression, we can use a neural network. So that's kind of where we're going. So again, as a data science practitioner, kind of your first goal when somebody asks you to do something is like, okay, what is it that I'm really trying to do? Like recognize, is it regression? Is it classification? Is it clustering, right? And then think, okay, well, these are the classification algorithms that I could use. right? Maybe an SVM is good enough for this data set. Maybe I need to train a absurd deep neural net on a cloud for 10 days. That once you know the problem you're trying to solve, then you can make that decision. But first you have to know, okay, if somebody gives you a data set and you're just like, okay, I'm going to use a neural net, like, for what? What are you trying to do? All right. So, yeah, so far we've talked about one unsupervised learning task. What was it? Clustering. Right. So we have our data. We're trying to group it somehow. We don't know ahead of time what the group should look like. Right. And hopefully we can all kind of see when that would be useful. Right? We want to, we'd like to be able to, describe these groups and understand how our data is sort of structured. Today we're going to talk about dimensionality reduction. Okay. And this is useful for visualization and a bunch of other stuff. It has a lot of applications. But here's the key idea. So I have a data set here. What dimension would you say that this data is? 2D. What about now? Yeah, it depends. So I could describe the points as 3D, right? They're positions in the room. We don't have like nice axis alignment stuff, right? But somebody said 2D. Why would you say 2D? It's still in a plane. Right? So in math terms, the embedding dimension is 3D, right? So the space here is 3D, right? But the intrinsic dimension, the amount of variation in the data, is really 2D. Right? And if I wanted to describe my data in terms of 2 coordinates and still be able to describe their 3D positions if I needed to, right? All I have to do is I add some axes to my paper. If I know my coordinates in terms of these axes, and I know what these axes are in 3 dimensions, then I can figure out the 3D positions of any point from these, even though I'm only storing 2 pieces of data per point. Okay. Another case of dimensionality reduction, on a point on the surface of the Earth, how many dimensions do you need to describe that? Kind of, probably you'd think of it as 2, right? But we're in 3 dimensions, right? So how did we lose that extra dimension? We know that we're on the surface of the Earth, and so the distance from the core or whatever we don't need to specify, and so we can get away with the latitude and longitude. So very often, right, we have data of very high dimensions, okay, but it isn't really the intrinsic dimension. The directions of variation are actually often a lot less than that. There's a few kind of applications of dimensionality reduction. So one would be compression. So for these points here, I don't really want to have to store 3 points per 3 coordinates per point. I'd rather store 2, right? Less data to store. So that's one reason. Another reason is if I want to understand the relationships between these points, knowing the 2D coordinates actually is much more useful for understanding how these points are related than the 3D coordinates, right? Because a third dimension is just kind of extra noise that's screwing stuff up. If I have a 10-dimensional data set and I would like to draw a picture of it, what plotting techniques have we talked about that work on 10-dimensional data? none. You could maybe argue that like a scatter matrix, sort of, right? But yeah, we can't. Humans are not going to visualize 10D data, right? We would really like to figure out the 2, maybe 3 most important dimensions, and then we can look at that. Okay? So there's a lot of reasons why the dimensionality reduction is useful. Okay? But the general idea is, right, we have some data that is, say, d-dimensional, right, and we want to figure out some m-dimensional representation where m is less than. Is this a supervised or an unsupervised learning problem? Unsupervised. How come?
Sure, what result?
Yeah, is there a right way to do this? You could think of like a million different ways to do this, right? You could change m, right? You could add more or less dimensions to your output. You could choose different ways of taking a d-dimensional point and turning it into an m-dimensional point. Okay. The data that we start with, is not labeled with what these points are usually. Right? We can come up with synthetic data where that's where we have some idea of how this should work, but we don't really. There's not a right answer here. Right? So this is again an unsupervised problem. Right? We're going to take our data and we're going to transform it into a lower dimensional data set and try to make sense of it there. Okay. So this is another unsupervised learning problem. Okay. So, any thoughts on how we might go about doing this? Maybe this piece of paper. So ignore, I don't know anything about the axes here. I just have these points that happen to be in space. Any thoughts on what I'm, how I could figure out that, like, oh, I want this to be flat? So these aren't the only 2 directions I pick, right? I could pick a really bad axis. What would be the worst, axis I could pick?
Why is this easier?
So if I picked an axis this way and used this as one of my 2 dimensions, that would be super, super bad. How come? Yeah. What would the coordinates that I store for this dimension for all my points be? So if let's say my origin is like right here, what is let's call this like the z-axis. What is the z coordinate of all of my points? 0, right? It's the same for all of them. What about if I choose this as my axis? What's the coordinate going to be there? It's going to vary a lot. Right? So does that give you any?
Look for variations.
So we look for variation.
For commonalities.
Yeah. So the directions that we want to keep are the ones where there's a lot of variation, right? And the directions we want to throw away are the ones that don't have any variation. Another important thing about this is we probably want these axes to be perpendicular. And this actually kind of gives us a nice algorithm. We can look for the direction with the most amount of variation. Pick that, and then just look at all the directions that are perpendicular to it. Right? So if I pick this direction first, the directions that are perpendicular are anything in this plane, and then I pick the one with the most variation in that direction, and that gives me my next axis, and then I can just go through and repeat this. Yeah.
Probably a breakdown of human mind, but we're showing 4 dimensions are still perpendicular.
Mm-hmm. Okay. So if I have let's say I'm in n dimensions, and I have k vectors that are perpendicular to each other. There are n minus k dimensions to pick the rest of the. So if I pick one axis in n dimensions, then I have basically n minus 1 dimensions to rotate in to pick the next one.
Which is why after in three-dimensional space, you have like a plane.
Mm-hmm. Yep, so in 3D, right, I have the first one I pick whatever direction, the next one is fixed to a plane, and then the third one is fixed. So the last dimension is always just the only one that's left that's perpendicular to everything else. So that's the idea. The simplified case here, what we're doing is we're really just kind of rotating the points around until we get like the x-axis in the direction with the most variation, and then the y-axis in the next most, and the z-axis with the least most. And then to get the dimensionality reduction, we can basically just throw away however many dimensions we want to. So in this case, if I throw away the z dimension, I lose pretty much nothing. Right? If I threw away the y, I would lose a lot, right? If I throw away the y, then basically everything kind of gets smushed to one line. Right? So I still get some information about it. I know how the points are distributed along that one line, but I've lost information about how they're distributed the other way. So that's the idea. So the particular technique we're going to look at is called principal component analysis, or PCA. And so the idea here is I want to find. So I have say n-dimensional data. And usually this is data where I'm using like a Cartesian coordinate system, right? So I have like x, y, z, w, whatever. So I have n-dimensional data, and basically what I'm trying to do is I'm trying to fit. I want to find n perpendicular axes here. Such that the points vary the most on the first axis, the next most on the second axis, the next most on the third axis, and so on. So the variation is most and so it's most along the first axis, and it's sorted all the way down. And the way I perform my dimensionality reduction is I only keep, so I figure out basically how far along each one of these axes my points are. Okay, so what I'm doing is I'm changing my coordinate system. Okay, and I get new coordinates for my points in this new coordinate system. Okay, and then I just keep the first however many axes that I care about and throw the rest away. So maybe let's look at a 2D example. So this is the data that I start with. Okay. And so the first thing I want to do is I want to find the direction of the most amount of variation, which in this case would be what? Not quite. So I actually have less variation along the x-axis than along a different direction. Actually, the direction where the points vary most is this direction. Okay, so the first direction I'm going to pick, the first axis I'm going to pick, is this one. Okay, the data is most varied along this one. And then my second axis is pretty limited, right? It just has to be perpendicular, so. Okay. So let's say this is my x-axis and my y-axis. I'm computing an x prime axis and a y prime axis. And and then I transform, I figure out, okay, what are the coordinates of my points in terms of x prime and y prime? So I have to basically rotate my points to this new coordinate system. Okay. And if I want to do dimensionality reduction, maybe I just throw away the y prime part. Okay. So my dimensionality reduction is I just say, okay, I take my two-dimensional points and my output is a one-dimensional point, which just measures how far along this axis am I. Does that kind of make sense? So what I'm doing, basically, I'm trying to rotate my axes so that if I throw away the higher dimensions, I lose not that much. So depending on, so I may want to be able to recover the original x and y positions. So I might want to be able to say, okay, I have a point that's, at x prime equals 3, and I might want to be able to go back to this as, x equals 2.5, y equals 2.5. And I might want to be able to go backwards, or I might not care. Right? Maybe this is for visualization, and once I throw away those higher dimensions, I don't care, and I'm not going to use it for anything else. If I do care about these, all I have to do is basically store the relationship between these axes and these axes. And if I know basically what this axis is in terms of x and y, then I can recover the x and y positions of my points if I want to. Does that at a high level kind of make sense? We're rotating, trying to find a new set of axes where there's most variation along my new x-axis, next most along my new y-axis, and so on. Yeah?
So I'm guessing that the effectiveness in keeping, or I guess in not losing a lot of information is dependent on the data set that you're doing this on.
Mm-hmm.
Because if you have ones that have too much variation, then doing this kind of dimensionality reduction would just use too much data potentially.
Yeah, so let's say my data looks like this. I have a perfect parabola. How many dimensions do you need to describe, points on a parabola? I'd say really just one. Like if you had a way of describing how far along it you are, that's all. If you know the equation of the parabola, you only need only one dimension. But if you try to run PCA on this, it's going to be terrible, right? Because you can't. There's no axis that I can fit on here that, if I throw away the other one, it's not going to help. So PCA, because of the way I'm doing the axis, only works. It only finds. It only does rotation. It can't do like curving or straightening or anything like that. Right? So PCA only, it's a linear operation. So it's not going to work well if I have something that's like curved that I'm trying to reduce. Like with this parabola, I can still run PCA. I get two new axes. I have no idea what they would look like in this case. Probably, I guess it would probably, I'd switch the x and the y axes probably. And I can store my points as long as I keep the coordinates of both of the, for both of those new axes, I can recover them, but I'm not reducing my dimension in that case, right? It's just another equally powerful, equally descriptive representation that takes the same amount of space to store. Right. So, so the way that this works is we're rotating our axes. To make this work, so rotation and translation kind of mix together in a weird way. So imagine, so really we want our data to be centered on the origin. So really when we're doing this, we actually want to subtract off the mean first so that our origin is in the middle, and then the axes rotate a little bit more nicely. So as a pre-processing step, usually we want to subtract off the mean, but I'm going to kind of ignore that for now. All right, so we'll talk about the math of how this works, and then we'll look at some examples where we're actually using this. So let's say we'll just talk about three-dimensional data for now. Okay. So if I have a point ABC, what this really means, or another way of thinking about it, is I'm taking my A coefficient, I'm going that far in the direction of the x-axis, and then in the B, I'm taking my B coordinate, I'm going that far on the y-axis. I'm taking my C coordinate, I'm going that far on the z-axis. Right? So this single vector, I can think about it as adding up three perpendicular directions, and that's the end result I get. I can do this with other directions, okay? And the goal of PCA is I want to find some new axes, W0, W1, W2, and new coordinates, T0, T1, T2, to describe the same point. And hopefully, I choose these in such a way that if I just ignore this, I'm pretty close to my original point. So as we talked about, we want to pick these W's so that as much of my variation of my data is in this direction W0 as possible. So what I want to do is I actually want to take the T0s for all of my points, and I want to pick a W so that the variance of the T0s of all my points is maximized. I want to pick the W so that I have the most kind of spread in my T0 coordinates. Okay? And so that's the goal here. So if I pick a W0, or I pick a W generally, the math to figure out what these T's are is actually really easy, as long as these are all perpendicular, which we're picking. So if I want to know what my new coordinate would be for my point, let's call this. So if I have some point W, and I want to figure out what the T's would be, that's a terrible one. Yeah. letters. Call it P. So I have a point P, and I want to figure out what the T's would be for that P, right? Or what the coordinates would be in this new coordinate system. It's actually really easy. I just take my point P, and I take the dot product with whatever axis I care about. So it's really easy for me to compute what these would be if I know what my W is. And so basically what I do is I optimize, I find the best W I can that maximizes the variance in T0. I pick the best, I try to find the best W0 to maximize the variance of this over all my points, right? And then I move on to the next one. So after I find W0, so I compute W0 that maximizes the variance of my T0s. Right? And then I compute W1, which is perpendicular to W0, that maximizes variance of T1. I compute W2, which is perpendicular to W1 and W0, which maximizes the variance of T2, and so on. So this is the way that the PCA works. So I'm trying to pick these directions so that as much variance as possible is on the lowest coordinates in my new space. And then at the end, I can just keep however many of the T's I need to describe my data. So this is kind of the same question we have with a lot of the methods we talk about. How many of these should I keep? So I can look at the error that I get. So I can throw one point away, figure out what. So if I have this point here, I throw away this part, and then I see how far away I am from my original point. Okay? And that tells me, what the error in my dimensionality reduction was. So over here, right, if I decide to pick one dimension, right, for this point, if I reconstruct that point, I'm going to be right here, and my error is going to be however far off I was there. As I keep more and more terms, right, the error is obviously going to go down. Right, I'm going to get closer and closer to the original point. And when I keep, I keep the same number of coordinates as I started with, I'm going to be, I'm going to get exactly the point. Right? So determining how many to keep, right, we can do something like elbow analysis, right, to see, okay, where do I hit diminishing returns? I might be limited by, I want to plot it, so I'm using 2D, right? But this is the same problem we have all the time, is basically how complicated of a model should I use, right? And we can use kind of the same techniques that we've used for other things. So this is PCA. That we're finding a new set of axes for our data, right? And we're trying to push as much information as we can into our new, x-axis, our new y-axis, our new z-axis, so we can throw away any of the other dimensions after that. So a couple of other ways of thinking about, yeah.
Is this sort of like, sort of analogous to the regression model where you're trying to simplify your line, so you're throwing out data you don't need? That when you're compressing your data with.
Yeah, so you could think of linear regression as almost like a 1D PCA, where you're like finding the one direction that you want to, that's like your main axis. You can kind of think about it like that. Another analogy is like when we're fitting the model and we're looking at, okay, I throw out this term, what happens to my R² value? Same kind of deal here. Okay, I throw out this dimension, what happens to my like reconstruction error? So when I take these reduced points and try to figure out how far away they are from the originals, right? As I throw away dimensions, I'm always going to add more error, but probably not that much until I like hit the real dimension of my data, and then my error is going to go way up. So yeah, some kind of parallels there. Okay. So a couple of ways of thinking about this. One way of thinking about it is we are rotating our data. So we're finding PCA is a way of finding basically the best way of rotating our coordinate system to align this data kind of how we want it. And another way of thinking about it is we're fitting an ellipsoid around our data. So I have this data set here. I can think of PCA as fitting an ellipse around this, and the axes of the ellipse are the axes of my new axes. Okay, so the major axis of this ellipse goes in this direction. The minor one is perpendicular. And so you can think about fitting an ellipse in a bunch of dimensions. When you get to the higher dimensions, right, it's going to be like smaller and smaller and skinnier, right? And those are the dimensions that we might throw away when we're doing a reduction. So kind of geometrically, that's what's going on. There's linear algebra, there's a bunch of connections to other things. But that's kind of the idea. Okay. Any questions about kind of the concept how we're doing this? Okay. So the x and the y-axis that we start with tends not to be just often not the best direction with the most information. So we're just trying to rotate to find out what are the best. So we're going to look at a couple of examples of how this is really useful, and we'll look at a couple of pictures that I think are pretty cool. So we will look at our old favorite data set and our new favorite data set. So our old favorite data set is, of course, the IRIS data set. Okay. So the IRIS data set, how many dimensions do we have? We looked at 2 a lot of the time, but we actually had 4. So there's the petal length and petal width, and the sepal length and the sepal width, right? And every time we plot, we're like, okay, well, we're going to pick just the first 2 for convenience, right? But they're probably not the best. Right, we're just plotting based on the petals. Right, we're ignoring the sepals, whatever they may be. Right, and so with PCA, we can actually take all 4 of those into account, and we're going to come up with 2 kind of directions that are like combinations of petal and sepal information. And so we're going to look at all 4 of those at the same time, right? And that's going to give us a much nicer visualization. Right? So if you remember, like every time we plot it, there's like 2 groups of irises that we can't tell apart because they kind of overlap. If we run PCA and pick our axes better, we can actually separate them, and it's kind of amazing. Okay, so that's the first example I've got. So yeah, all of our boring stuff. So here's some math on PCA. Yeah, we don't really care about that so much. Right, we're going to look at the IRIS data set. Right, we have these 4 dimensions in our data, and we're going to reduce it down to 2 with PCA. right? And then we can run our other analyses on the reduced dimension stuff. We can visualize it, all sorts of nice stuff. So I got our iris data. And again, if we just look at the first, two dimensions, we see the blue and the green are all mixed together, right? We're only looking at the sepals, I guess. We're not even looking at the petals, which I assume are the more important part. But, yeah. So, right, these two dimensions that we're starting with aren't that great for our tasks of telling the irises apart. If we look at the first 3 dimensions, maybe that's kind of better, but it's 3-dimensional. It's really hard to tell. For this to be useful, I'd really want to be able to rotate this image, but the incantation to do that in a Jupyter notebook makes everything really crappy. So, right, working in 3 dimensions is not great. So, we can also look at the scatter plot matrix. Right, so now we're looking at all 4 of the dimensions, which is all the data is there, but it's kind of overwhelming. If there's relationships between more than 2 of these dimensions at a time, we can't really understand that from this picture. Right? So again, this doesn't really solve our problem. And if we had more than 4 dimensions, right, this would get increasingly useless. Okay. So what we're going to do is we're going to use PCA, and we're going to find the 2 best dimensions, the 2 dimensions with the most variation in the data, and we're going to plot them. Okay. So we're going to fit a PCA. Again, this is unsupervised, so we're only looking at the x's. Okay, so the y's don't show up here. So this is just, okay, what combination of petal and sepal length and width has the most variation along it? If we look at that, then we see that for these 2 dimensions we picked, we could do logistic regression to tell blue and green apart. Right? We now have a nice decision boundary between these 2, which we had never seen in any of the other visualizations that we saw. Okay. So, this picture here should be like, oh, we actually could do a pretty good job of classification here. Whereas the pictures before, they're like, well, everything's so mixed together, how would you know? Well, yeah, this shows us that we should be able to get pretty high accuracy on the classification. One thing we can do is we can take our new PCA data and use any of the other algorithms we have. So here's a so here we're using the original data, but we're just going to use this PCA to visualize it. So we're just going to do a hierarchical clustering like we did before, but now when we visualize it, we'll use the PCA coordinates. Okay? And you'll see that this gives us a much better, much easier to compare our expected to our clustered results. You can see we're not totally capturing it. We're not really capturing the diagonal part here, but we can actually see that now, as opposed to well, there's some blue and green dots that are overlapped, and I don't know what that means. And we hit 80% accuracy. So that's pretty good. So for plotting, for looking at this data visually, right, two dimensions of our reduced data is very convenient, right? But if we're going to do something else, right, we'd want to know how, if we're going to take this reduced data and feed it into an SVM, right, we'd have to know how many to include. So here we're going to do basically elbow analysis. So here is the amount of the variance explained. And basically what we're looking here is, this is like the variance of the T0s, the variance of the T1s, the variance of the T2s, the variance of the T3s. Okay. So we can look at, you see that, oh, probably for this data set, we could use one principal component and capture most of the variation in the data set. Okay. And if we look here, that's probably true, right? Look, almost all of the variation is along this direction. If you look at the scale, it's even more obvious, right? This goes from -3 to 4. This only goes from, this is like much smaller variation. So for this data set, one principal component tells us a lot. And if we were going to train a classifier on a 1D thing, right, we just put a line here and a line like here, we're actually going to do pretty well. Yeah.
So if we're going to use the eyeball to decide which point shall we stop, we can see that is 2 principal component 2. That is where the variation won't drop any more obvious.
So this one actually, so this is how much of the variance is explained here. So this is maybe not exactly the elbow. This is kind of the usefulness of each dimension. So this one is very useful, this one is not very useful. So it's not exactly the same as, it's not a cumulative thing like the elbow for like k-means. So it's maybe yeah, it's not exactly the same thing data that we're looking at.
So visualization makes sense to me, but why would you do analysis after you get that your principal analysis? Like you're losing data kind of inherently, right?
Yeah, but if I want to train a classifier, maybe I don't need all the dimensions.
I guess the classifier, it's possible that you would get like kind of lucky, I guess, and it might be better based on less data, but that's still less accurate.
Yes, so you'd be trading accuracy for speed of training and speed of prediction. So if I have a complicated model, so when we talk about like neural networks, right? If we have tons of dimensions, we have like hundreds or thousands of parameters to tune when we're training our networks, right? If we do a dimensionality reduced one, we can cut that down by a lot, so we can speed up training, or we can speed up prediction. So it can be very convenient to work with fewer dimensions, just from computationally or data storage or whatever else. So think about like KNN. So I train a KNN classifier in dimensionality reduced points, right? Each point in my acceleration structure is smaller dimension. So that's going to be big space savings. So yeah, if we're interested in how many dimensions to keep, this is just like the standard deviation of my T1s, the next coordinate, and I can see when this gets to be 0, right? Then I can just kind of throw that away. Another useful thing is to look at is to actually look at what the principal components are. We'll do that for the next data set we'll look at, which is the handwritten digits. So it's kind of cool what those look like. So we've seen the handwritten digits. What dimension is this data in? So how many numbers do I have to store per image?
64.
Like 64, right? I have 8 by 8, right? So I have 64 numbers, right? How bright is each pixel? Right? 64 dimensions, that's a lot of dimensions. Right? I would love to deal with many fewer dimensions. Okay? So let's see if PCA is a useful thing. So we got these are our handwritten digits. Cool. So we'll just look at a few of them. remind you what they look like. Okay, so again, 64 dimensions, right? Probably we don't need all those dimensions, right? So like, especially like the points around the borders here, like that's probably not a lot of useful information for like a classifier, right? So there's probably, you know, another thing, like if we have just kind of like staticky noise, that probably also isn't very useful to us, right? But some of the things that are important would be like, you know, like a vertical line of points, right? That's kind of like, you know, if I have like a line, right, that means I'm probably a 1 or a 7. And so there's some features like that that are probably pretty important. And so we'll look at exactly, you know, what the principal components of these images are. Kind of an important thing to remember, this is data dependent, right? So if I took a bunch of images of letters that were the same size, right, I'm going to get totally different principal components, right? Because the data is just, it looks different, right? So this is very dependent on the actual data points I have, not just the dimension, it's the data itself. So, so we're going to do PCA. We're just going to look at 2 components. So we're going to throw out 62 dimensions, okay? And we'll see how we do. So we're going to fit a k-means clustering to our 2-dimensional data and see how we do. So we'll look at the decision boundaries. So this is all stuff to draw the nice colored stuff and do the prediction, draw the decision boundaries. Yeah. So we're going to just draw this. And then, so this is the picture. So our accuracy, our homogeneity that we get is 45%. So that we've thrown away all but 2 dimensions of our data. So we picked 2 dimensions out of our 64, 2 directions out of our 64 dimensional space that we decided were important. And we're getting like half of the digits in each cluster are the same, right? Which is pretty good, right? Out of, you know, we're trying to distinguish out of 10, right? And we've thrown away so much of our input data. So this is kind of amazing that this is good. And we can actually see, you know, how we split up. So here's our centroids. Here's our points projected into this space. The clustering doesn't look super great, but you can see like there's definitely some tight groupings in here that indicate to me that the, you know, it's images that are going to be pretty similar. If we look at and then these are the actual principal components. So let's actually going to draw these. So I'm going to draw. I'm going to draw just the first principal component. So this is the axis that I picked for the first one. And let's look at the second one. I'm going to split these into 2 cells. Okay, so these are the two, so this is the first dimension, right? It's like a mix of, I don't know, maybe the stroke of the 7 and maybe some 4 and some 9 stuff mixed in there, right? And depending on how we mix these with whatever this stuff is, right? Somehow the mixture of these two patterns can get us pretty good accuracy on this data set. Right? Kind of crazy, right? But these two sort of patterns seem to be the most important, parts of these images. Anybody, if I had asked you to come up with like the two, would anybody have drawn something like this?
Obviously.
Yeah, pretty obvious in hindsight. Yeah. Yeah. So this is just a two-dimensional PCA model, right? Our clustering and stuff that we did is going to be faster because we're only looking at 2 dimensions when we do it. We can visualize it, and we still actually get an insane amount of accuracy. Let's go a little further. So we're going to fit a full PCA model, so we're going to fit a 64-dimensional thing. Okay. And what we're going to do here is we're going to look at the all 64 of the components. So we'll see the most important all the way sorted to the least important, and it's kind of interesting what happens here. So these are the two that we already saw at the top. Right? So these are the ones we saw. Right? The next couple are like kind of big regions, I guess, are indicative of some of the numbers. Okay? And as we get down to here, right, from here basically down, it's just noise. Right? So, this doesn't tell you anything about, which digit we're looking at. It's just noise. Right? So it makes sense that throwing away all of this stuff is probably going to cost us like nothing. In terms of our accuracy, it's not useful information. We can just discard it, and we'll save memory, and we'll see examples of doing denoising. So we can fit a lower dimensional version of something, and then upscale it back to the original, convert that reduced coordinate thing back to the original, and what we lose is like static, right? So it's actually beneficial that we lost it. So these are what the principal components look like. These ones the last two are pretty weird. And again, these are sorted based on like how, about how much they show up in the various images. So these ones are just basically the coordinates in those dimensions are 0.
Did you mention how your 64 dimensions were generated here?
So we have 64 pixels. So each pixel is a dimension. And so we just ran our PC algorithm until this weird single pixel here, right, is the direction that is perpendicular to every other image on the screen, if you think about them as 64-dimensional vectors. So we just, so here we found the direction with the most variation, and then this one is perpendicular to this somehow. And I can't think in 64 dimensions, but it's perpendicular, and it has the next most variation, and this has the next most variation, and so on.
I guess I have a disconnect between how the individual pixel has been translated into the dimension.
Oh, so this is if you think about this, is a 64-dimensional vector of numbers from 0 to 255. I've just split them out into rows. So it's just a 64D vector that I'm viewing as a picture. Yeah. Yeah. So this is agnostic to the relationships between pixels. So I'm not putting any information in here. I don't care about like whether things are adjacent or on the next row or diagonal. Nothing. Just like I have 64 dimensional points, linear algebra, do stuff, right? And I get back 64 vectors, and I can use those for dimensionality reduction. Okay. So yeah, it's kind of, this top row is like kind of the useful information, right? And you can imagine after this, basically, if I threw those coordinates away, I'm losing nothing. Cool. So if we fit on the full PCA, we expect that the homogeneity score, you expect to go up a little bit. Yeah, it went from like 50% to 67%. So and now I'm keeping all of the dimensions, but so that's probably overkill. But, and then what I'm doing here is I'm actually plotting the centroid point of my cluster, and I'm plotting how much. So my centroid point is a 64D point, okay? And each coordinate in that point tells me how bright to make the corresponding PCA component. Does that kind of make sense? So what we're doing here is it's basically showing. So this I get by adding up all of the. It's a weighted sum of all of these. So I'm just picking my centroid. Basically tells me what the weights for each one of these should be. And what I'm drawing here is the weighted contribution from each component. So if we look here, the 5 is mostly made up of these 4 principal components and 0 values for everything else. So if we look at, so like all these noise components, there's the coefficients are 0. Does that kind of make sense? So this is kind of a way of visualizing my centroid. So this is, the middle of the 5 cluster, right? And it's made up of these 5 components. This looks like it's my 6 cluster. And after here, right, if I look at more than like 10 dimensions or 16 dimensions or whatever, they have no, their coefficients are all 0. I'm not adding noise to these images. Right? I think that's a 7. It's hard to say. Some of these are pretty weird. I think that's a 1. That one, 0 is pretty good. It's made up of a few of these ones mixed together. Okay. And so by, the PCA lets me pick these basis images that I can add a few of together to get any of the points in my data set. So yeah, the 2, 1 is, the 2 is a mixture of these ones. I assume that's a 4. Not sure about that. Other 2. So it doesn't look like it was perfect, but this gives you kind of hopefully this gives you kind of an intuition for what's going on. Yeah.
So there's probably some optimal number between 2 and 4 that's determined by this.
Yeah, I would guess that after, I don't know, probably after here. So if you after 16, probably. If you looked at the homogeneity score as a function of the number of components, I bet it would be 1, 2, 3, 4, and then it would pretty quickly flatten out, I would expect. Cool. So this PCA, it's kind of the simplest form of dimensionality reduction, right? It's just rotating the axes to find the best directions with the most information, and we can reduce the dimensionality by throwing away the ones that don't have that much information. So in this case, right, these were the noise directions were, you know, useless. So we can just throw them away, and we're not really losing anything. Yeah.
First, I agree. When we looked at this data set before, we were just doing it clustering.
Yeah.
Clustering on the raw
So,
data.
so we were using the X, just our axes. Our first axis was brightness of the top left pixel. Our second axis was brightness of the second pixel. Our third axis was brightness of the next pixel. And so that was the coordinate system we were using.
This was a couple weeks ago, right? I
Uh,
was just trying to figure out what the accuracy of that model was.
Oh.
Why this is so bad. I
Um,
thought that was pretty accurate.
yeah, I don't know. The accuracy is probably similar. This gives us a lot more understanding of what the model is doing, right? Being able to see what the components are, and especially like what the clusters look like and how they're like put together, is pretty cool. I think that gives us you know, understanding of like, okay, how does this actually work? Like what is it that we're looking for when we're clustering?
I'm just trying to figure out what the trade-offs of using this versus that, or speed or space, or.
So looking at this and looking at, you know, cluster centers, we can see that we don't need all these dimensions. So we could boost our speed by doing PCA, throwing away half the dimensions, and then doing whatever algorithm on what's left over. Right. Okay, so there's a new homework posted. It is substantially shorter than the last one. If you're not quite finished on that, we'll set the like due date tonight. If you need to take the rest of the week, we'll take off a little late penalty, but still worth your time to work through it. The homework is about classification using the various scikit-learn classifiers that we talked about. And so one, you'll be looking at the digit data sets, and then also we have another data set about online movies. I will see you tomorrow.